Okay, so here's the first example, and maybe there should be an example 0 if I have the geometric series that we already looked at, an equal to 1, then the sequence of ratios is always 1, so you get the exponential growth rate is 1, which implies the radius of convergence is also 1, which we already knew, namely that this series converged on the unit disk, and so its radius of convergence is 1. Okay, but here's a more interesting example. If the ANs are just n, the sequence of consecutive ratios is n plus 1 over n, and this tends to 1 as n goes to infinity. Our previous theorem says you can use this also to show that n to the 1 over n tends to 1. There are various ways to prove this from scratch, but it's nice to see that our general result just gives us this fact, and we're going to use this in future examples. Okay, but then now that this sequence of consecutive ratios converges, this is our exponential growth rate, and it's clear that intuitively at least that n has no exponential growth at all. So it doesn't decay exponentially, it doesn't grow exponentially, it kind of is what you might call a sub-exponential term. So its exponential rate of growth is just 1. Okay, and that tells us that the radius of convergence of the corresponding power series is 1 over rho, which again just happens to be 1. So like I said, sub-exponential terms have no effect. So here's a whole family of examples. So if I have a power series here and I throw in terms of the form n to the k, these do not change the radius of convergence of the original power series. Why is that? Well, you can use the lim sup calculation that when we look at the lim sup of these roots, well, the first part, n to the k, will look like n to the 1 over n to the k, and the other part will be the an to the 1 over n, and we just pointed out that this part goes to 1. So in the lim sup, this part's going to go to 1, and so the result will just be the exponential rate of growth of the ANs. So the point is, this power series has the same radius of convergence as the original one. So putting in n to the k here, k is just going to be a natural number, but you could also take it to be an integer. If you have negative powers in here, you might want to avoid n equals 0, so that's this case down here. But you can also use this to show that if I put in p of n, where p is a polynomial, that this new power series will have the same radius of convergence as the original one. This result here will require a little work, so maybe it'll be an exercise, but the growth of this will be dominated by the top degree term in the polynomial, but it's not going to change the radius of convergence. Let's look at another example. Let's consider an is n factorial, so n times n minus 1 dot 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 all the way down to 1. So n factorial grows really fast. In fact, its exponential rate of growth is infinity. We can show that with using consecutive ratios. The consecutive ratios would be n plus 1 factorial over n factorial, which is just n plus 1, and that goes to infinity. So that tells us the exponential rate of growth is infinity. We also get out of this that n factorial to the 1 over n tends to infinity as n goes to infinity. And we get that the radius of convergence of this power series is 1 over infinity, which in extended reals we count as 0. Okay, but if you use instead the sequence of 1 over the factorials, you can flip everything above, and you get that 1 over n factorial has exponential growth rate 0. So this power series has radius of convergence infinity. So this converges for every z in the plane, and it converges absolutely. Let's look at a fourth example. This one looks a little contrived, but it shows why you might want to use the root test or the root computation to find the exponential growth rate. The ratio test seems quite convenient, but it doesn't deal with zeros very well. So consider the following power series. N goes from 0 to infinity, and the coefficients are 3 to the n, and I'm using certain powers of z. I'm only using powers of n squared. So the series will look like 1 plus 3z plus 9z to the fourth, and then the next power of z would be z to the 9. And so this actual coefficients of the corresponding power series, they don't have a nice formula, but an is 0 when n is not a square, and 3 to the m when n is a square, m squared. And how do you compute the lim sup of these an to the 1 over n's? Well, lim sup, which we haven't really reviewed, but it computes the limit of subsequences whose limit is as large as possible. So when taking the lim sup of a sequence, you might as well switch to any subsequence that consists of non-zero numbers. So you can throw away zero terms, certainly when computing the lim sup, as long as there's infinitely many of them, because you're not going to get the limit, the largest limit from a subsequence if you throw in the zero terms. There's just no reason to. So you can take lim sup of the worst subsequence, the fastest growing subsequence, and so for that I'll only use these terms where n is a square, and so for that you'd have 3 to the m to the 1 over m squared, and so this will be 3 to the 1 over m, which goes to 1 as m goes to infinity. So you get the radius of convergence, or I guess the exponential growth rate of the sequence is 1, so the radius of convergence is 1. Finally, let's prove this fact that the exponential rate of growth of the sequence is 1 over the radius of convergence of the corresponding power series. So this was item C in the theorem from 2 slides ago. So here's the proof. Let's first show that 1 over the exponential growth rate is less than or equal to the radius of convergence of the power series. If rho is infinite, there's nothing to show because the left side is 0. So let's assume it's finite, and let's take a number b bigger than rho. And by the definition of exponential growth rate, that means that the sequence is bounded by powers of b to the n, maybe with a constant in front. Then we can use this to establish that the power series converges for some z's. So here's the sum of the absolute values of the power series. I can bound an by a constant times b to the n and get this. And then this will be finite when b times modulus of z is less than 1, which is this condition here. So that tells me that the radius of convergence is at least 1 over b. Now b was an arbitrary number bigger than rho, so I can take a limit as b goes to rho to get this lower bound. Next, we establish the opposite inequality. So now we show that 1 over the exponential growth rate is greater than or equal to the radius of convergence. So similarly, if rho is 0, then we take this side to be infinite and there's nothing to prove. Else, assume it's non-zero, and we can find a number smaller than it. We better take it to be positive. And as we said earlier, if you have a number smaller than the exponential growth rate, then you have to have an greater than or equal to b to the n for infinitely many n. And using this, we can show that the corresponding power series actually diverges. So consider the sum of the absolute values. This is greater than or equal to the following sum. I'm going to restrict the sum to n's for which star holds. So there's infinitely many of them. So when star holds, I can bound an below by b to the n, and so I get this inequality here. And this will actually be infinite when all of the terms are greater than or equal to 1. That's clear. If all of the terms are bigger than 1 and there's infinitely many of them, you get infinity. And so you get that the series diverges for z greater than or equal to b, 1 over b in modulus, I should say. So the radius of convergence must be less than or equal to 1 over b. And b was an arbitrary positive number less than rho, so we can take a limit as b goes to rho to get the opposite inequality. Putting together the two inequalities, we get that this inverse relationship between the radius of convergence and the exponential growth rate.